This is the first of the homework week 2 assignments I want to talk about, just to give you an idea of some of the things I'm looking for and some of the things you might find interesting about the results from this particular assignment. First, notice in this particular submission, there's a stratified sample set of results, a second set of results with a separate seed, and the natural distribution. So let's start with the natural distribution, because this is where you normally start when you are building predictive models, or at least you might want to start this way. And so the first thing to notice is on the right side, when we look at precision, recall, specificity, and sensitivity, it looks like it's calling everything the same value. And when we look at the accuracy at 94.9%, that should look suspiciously like the 94.9% zeros in the data. So what's happening is the algorithms are calling everything a zero. But as I talked about in the stratified sampling video, that's not the full story of what's going on. And we can tell that because we look at the ROC curve, area under the curve, we're getting values, 0.616, 0.5s for these other models. In fact, this 0.616 is interestingly better than the area under the curve for the stratified sampling, even though it's just barely. So it's probably not statistically significant. The first decile lift is very good, on par with the others, a little bit better than the first stratified sample, etc. So these classifiers are clearly doing something. They're not merely degenerate when they say call everything a zero. It's related to that threshold issue I was describing before. So the models are still doing something, especially logistic regression and the neural network. The trees are more susceptible to doing something that's uninteresting and not useful, because maybe you'll just get one or two splits at most from the natural distribution with the trees. Let's go now to the stratified sampling results, just to look at some of the differences that we're seeing here. First thing to notice is the logistic regression, regardless of the seed, it's getting approximately the same kinds of results. So 6150, 6157, and that's good. Changing the seed should not change the models significantly, or else we have a real issue with just the randomization of the original data. Now we're going to see that to some degree with the neural networks. Neural networks are susceptible to the initial starting position. So sometimes when you shuffle the seeds to generate the neural networks or for the data, you will get different results. And we're seeing that a little bit. The lift, the 10% depth, you can see is different between the one seed and another seed. So you do have to be a little careful. It doesn't mean that those neural networks are not valid. It just means they're finding a different path to the answer. So that's the first thing to notice, is the stability of logistic regression and the variability with the neural networks, and to some degree the trees are different when you change the random seed. And trees are notable in what they're called unstable predictors, because they small changes in the data can produce significant changes in the decision trees themselves. So let's look at one other aspect of this. So when I highlighted in red what I found to be some of the more interesting things here. One model, the specificity is 75% and the accuracy is 73%. That's for this neural network with one hidden layer and two neurons. So it looks on its face like the accuracy is better, but we should already be suspicious of this quote-unquote accuracy number. As we know, we are able to get 94%, 95% accuracy just by calling everything a zero. And what's probably the case with this is these are just calling more zeros, calling more results zeros. So it's getting a higher proportion of the zeros correct. Where in this case, we're probably more interested for our marketing problems, and the same thing's true for fraud detection. We're probably more interested in a rank ordered approach. So area under the curve, for ROC curves or for lift curves, is probably a better way to measure what's going on with this model. And you can see that at the 70% depth, it's basically a coin flip. Lift of 1. You're not doing any better than you would at random. At the 10% depth, it's 0.76, It's just it's not doing well. In fact, this model is probably flaky, bouncing around, because if the lift at the 10% depth is smaller than the lift at the 70% depth, then we're getting some strange behavior indeed. That it's that if we looked at the lift chart, it would probably be jumping around as you go decile to decile. So those are a few things to be aware of when you see an actual lift chart, and maybe I'll show you an example of this later. It should be monotonically decreasing, not just the cumulative, but the decile to decile lift should be monotonically decreasing. Higher lift with the higher scores, the lower decile numbers, deciles 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have the highest lift at decile 1 and the lowest lift at decile 10, even when you look at just that 10% population like this summary chart does at that particular depth. So be careful. If you see that kind of flaky behavior, you know you have an unstable model. I guess those are the only things I want to mention from this particular homework assignment. If there are additional questions, I can always address those at a later time.